Hi there. So our next topic we're going to get into is going to be in Chapter 9. I'm going to break Chapter 9 up into two separate videos. My first video is just going to be on sections 9.1 and 9.2. And then I will make another video on 9.4 and 9.5. One of the things that you're going to see when you go in and do your online homework is that it's actually all put together in one big homework assignment. So we're just going to touch on some of the ideas in Chapter 9 here. And what we're going to touch on are differential equations. And differential equations are actually one of the most important applications to calculus. Physical scientists use them, social scientists use them. They're used when modeling various phenomena, okay? So what is a differential equation? It's an equation that contains some unknown function and some of its derivatives. Now, why is it not surprising that these things come up a lot? Well, a lot of real-world problems come up when changes occur, and we want to predict future behavior based upon these rates of changes. Well, by definition, a rate of change is the derivative. Okay, so population growth, motion of a spring, the list goes on. Okay, so in general, a differential equation contains some function and one or more of its derivatives. Now, we can talk about the order of differential equations. The order is just the highest derivative that occurs. In this class, we are just like not even going to barely touch the surface of differential equations, but we're only going to be talking about first order differential equations. The last thing I want to say as an intro to this is that a function is a solution of a differential equation if the equation is satisfied when the function and its derivatives are substituted in. Now, when solving a differential equation, we want to find all possible solutions. Those are called a family of solutions. And then the last thing I want to note is that we're only going to be talking about two sorts of differential equations in this class. But in general, solving differential equations is not easy, and there's no systematic way to solve many of the differential equations. So, let me talk about how to set up some basic differential equations, and then I'll talk about how to verify whether or not various functions are solutions to differential equations. So again, this is on 9.1 and 9.2 specifically. So what I'm going to do is just go through various examples here, okay? So let's suppose we have a fish population, and our fish population increases at a continuous rate of 20% per year. And further, suppose the fish population is decreasing due to fish being harvested, caught, or just dying, let's say, at a constant rate of 10 million per year. And what we want to know is, how does the fish population change with time? Well, I claim we can start by saying that the rate of change of our fish population is going to be the rate of increase due to breeding minus the rate of decrease due to harvesting. Okay? Now, what are we going to call the rate of change of fish population? Again, I could say my population is a function of time. We've seen the notation P prime of t, but recall another notation that we use. The Leibniz notation is, we can say that's equivalent to dp dt. Okay? Be ready to see either one of those. So the rate of change of our fish population, dp dt. All right, let's talk about the rate of increase. Notice it's increasing at a continuous rate of 20%. 20% of what? Notice it's 20% of the population. So the way we would write that is 0.2 times p. There's my unknown function. Okay? Minus a constant rate of 10 million. So we would say minus 10. And I'm just going to note that P is the population in millions, and T is our time in years. Okay, let's take another example. What if another example is the amount of money in a bank is increasing at a rate of 8% of the current balance. Can we write a differential equation for the rate at which this bank account balance is increasing? We absolutely can. I'll just call it dB dt. Notice we're only talking about it increasing, which is fortunate when we're talking about money in a bank. And it's increasing at a rate of 8% of the balance. Okay, why do I keep emphasizing this? Because such a natural thing for folks to do is to put T here and similarly T over there. Okay? All right. What if I have this guy? What if now I tell you that a yam is placed in an oven, which is at 200 degrees Celsius, and the temperature, we'll call that Y, of the yam increases at a rate proportional to the difference between the temperature of the yam let me say between the oven temperature and the temperature of the yam. All right. So how would we write this as a differential equation? Well, it's a differential equation, so dy dt. Okay, let's translate this. Okay, it increases at a rate proportional to. Okay, whenever we talk about proportionality, remember we have our constant of proportionality, k. In this case, we don't know our value of k, so we're just going to call it k. Well, what is it proportional to? It's proportional to the difference. Difference means subtraction. And the difference between the oven temperature, which is 200, and the temperature of the yam. Okay, one last example here. What if I tell you that a radioactive element decays at a rate proportional to the amount present. Can we write a general differential equation here? And I claim we can. Okay? We'll just say it's dp dt. And I claim we don't know what the rate of decrease is, but we can certainly say that it's k times p. Now, one comment that I want to make, k is negative. Why is k negative? Again, because it's decaying. It's just something to keep in mind. All right, so that gets us going and warming up with setting up some of our differential equations. Now, what I want us to do is learn how to verify whether or not a function is a solution to a differential equation. Okay? And the nice thing about this is it's very similar to verifying that something is a solution in algebra. Okay? For example, how would you verify that x equals 3 is a solution of, I don't know, 5x minus 7 equals 8? Okay, how would you verify that? Well, wouldn't you take x equals 3, plug it in, and check to make sure you have equality? The same thing happens here. Okay, so in order to verify that a function is a solution to a differential equation, you're going to want to plug in the function and the derivative. Okay? So, let's take our first example. What if I want us to verify that y equals 2x minus 4 is a solution to dy dx equals x minus 1/2 y. So right now I'm telling you, hey, this is a solution. I just want you to verify that for me. Okay? Well, how would we do this verifying? What we would do is as follows. We would find dy dx and plug that in here. And we also have our function y. We would plug that in here. So first off, I think you'll grant me that if y is 2x minus 4, dy dx is equal to 2. You got to go back and celebrate taking derivatives like that again. Okay? So what I'll do is I'll plug that in. Notice dy dx is equal to 2. And I want to know, is that equal to x minus 1/2? Well, y here is 2x minus 4. So this is what we want to verify. And I claim that we can distribute the 1/2. Minus a negative is plus a positive. And we get 2 equals 2. And we'll say, yep, we verified that that's a solution. Okay, this is the sort of thing that we're going to want to do here. All right, so let's go back to that YAM example. Okay, recall that YAM example. We got the differential equation dy dt was k times 200 minus y. Okay? That was the differential equation that we found just moments ago. Now what I want us to do is to verify that y equals 200 minus c e to the negative kt is a solution. All right, well, I told you what the solution is. Let's actually see how we can verify it. Notice to verify it, what I need to do is plug in my derivative and plug in my original function. So let's look at the left-hand side, the derivative, dy dt. Well, if that's y, we can certainly take the derivative. The derivative of 200 is just 0. And what do we get there? Negative c, and then the derivative of e to the negative kt is e to the negative kt times negative k. So we get ck e to the negative kt. Negative times negative is positive. So that's our left-hand side of the equation. Now let's look at our right-hand side of the equation. In other words, let's see what we get when we plug in y. Well, we have 200 minus y. Y in this case has more than one term, so I'm going to need to put that in parentheses. Next, I'll distribute the negative sign throughout my parentheses. Notice my 200s cancel, and again I'm left with ck e to the negative kt. Notice that my left-hand side is equal to my right-hand side. Okay, so we have verified that that is the solution. Now, I want to give us one more little piece of information with this YAM example, just to take it a little bit further. Okay? Suppose I gave you an extra piece of information, and this extra piece of information I'm giving you is what we call an initial condition. And my initial condition says, hey, initially, in other words, at time 0, the YAM was 20 degrees Celsius. Okay? Can we refine our solution a bit more? And I claim we absolutely can. We know y is 200 minus c e to the negative kt. So what will that give us? Well, we're given that when t is equal to 0, my temperature is 20. So what do I get? I get 20 is 200. Okay, e raised to the 0 power is 1, so minus c. So we can subtract 200 from both sides to get negative 180 is negative c, or c is 180. So while we saw that this is our general solution, what we can say is, given this initial condition, my particular solution is 200 minus 180 e to the negative kt. All right. So the next example that I want to show you is a couple more of verifying that things are solutions or not. So let us look at this. Suppose I have this differential equation, x times dy dx minus 3y equals 0. I'm going to ask, is y equals x squared a solution to this differential equation? And then, after we answer that very interesting question, I'm going to ask, is y equals x cubed a solution to this differential equation? So let's go through that. Okay, in order to verify whether or not something is a solution, we need to plug in the derivative as well as our function. Well, I think you'll grant me if y equals x squared, dy dx is 2x. So let's plug this in and see what we get. Okay, if I plug this into my function, my differential equation up here, I have x. Now dy dx, we got to be 2x minus 3. And notice y here is x squared. and I want to know, is that equal to 0? Well, is 2x squared minus 3x squared equal to 0? Nope. And therefore, is that a solution? No. Okay? Now let's do the same thing over here. We have y is x cubed, so dy dx is 3x squared. And now I'm going to take these values again and plug them in my differential equation above. So I have x for dy dx. I plug in 3x squared minus 3. And for y, I plug in x cubed. And I want to know, is that equal to 0? Well, is 3x cubed minus 3x cubed equal to 0? Yes, it sure is. Therefore, y equals x cubed is the solution to this differential equation. All right, so for this last example, what I want us to do is kind of play a matching game. So here's what we're going to have. Suppose I have the following differential equations. dy dx is y over x. dy dx is 3 times y over x. dy dx equals 3x. dy dx is y. And finally, dy dx is 3y. Okay, those are my differential equations. Now, I'm going to make a list of functions in a second, but I just need to make a quick comment here. Okay, especially these two. Notice what we're saying here. We're saying that the derivative of our function is the function itself. I hope you're all thinking e. Okay? And what I'm saying here is that the derivative of my function is 3 times my original function. Okay? So, suppose these are our functions. So we have function 1 is y equals x cubed. Function 2 is y equals 3x. Function 3 is y equals e to the 3x. 4 is y equals 3e to the x, and function 5 is y equals x. Okay, so what I want us to do is match the solutions and the differential equations, but I want to make a comment that each equation may have more than one solution or no solutions. So this isn't a one-to-one matching game. All right, so the way I would begin a problem like this when there's a bunch of matching is I would take my derivative. Think you'll grant me the derivative is pretty relevant. So here we have dy dx is 3x squared. Here we have dy dx is 3. Here we have dy dx. Well, it's e raised to that power times the derivative of the power. Here we have dy dx is 3e to the x. And finally, we have dy dx equals 1. All right, this should at least get us going in terms of doing the matching, okay? So, the first one, dy dx equals y over x. Well, what we want to do essentially here is we're saying that our derivative is equal to our function divided by x. So for example, if I take my function here, x cubed, and divide by x, I get x squared. Okay? So, is this the case here? No. Okay? Now, let's ask ourselves, does this first function satisfy anybody else? Well, is it equal to 3 times y over x? Well, notice y over x is x squared, and our derivative is equal to 3 times that. So function number 1 fits in here. I think you'll grant me function 1 does not match here. We don't get 3x. The derivative was not equal to the function itself, nor was the derivative equal to 3 times the function, or we'd get 3x cubed. All right, let's see if this matches any of them. I think you'll grant me that it does not satisfy this. 3 is definitely not equal to 9x. The derivative was not equal to the function itself. The derivative was not equal to 3x. So let's see if it satisfies one or the other here. Well, let's look at what y over x is. Y is 3x, x is x. So we have y over x is equal to 3. Okay? Well, does that satisfy either one of the two above? Well, y over x is 3. Was our derivative here equal to 3? Sure was. So therefore, number 2 works here. All right, let's mosey on down. I think you'll grant me that neither one of these are going to work for our first two, primarily because y over x, we'd have an e to the 3x over x, and that's just not part of our derivative here, okay? Also, in neither case were our derivatives equal to 3x. So let's ask ourselves, does this satisfy this function here? Well, was our derivative equal to the function itself? No. But isn't our derivative equal to 3 times my function? Sure is. So number 3 works here. Notice number 4, wasn't my derivative actually equal to my original function? Therefore, that goes there. And does this satisfy any of the above? Well, let's look. dy dx, let's see if it works for above. Y is x, x is x. Is y over x, 1, equal to our derivative? It sure is. So number 5 also works there. All right. Well, I hope this gets you going. And then in the next video, what we're going to talk about is 2 specific types of differential equations. Thank you.